Будет оно сложное.
В общем, кодификация и узлы. А вы русский все-таки или английский читаете?
Что?
Русский или английский?
Вы что вы читаете?
Как заказывает аудиторию?
Ну давайте, но если вы свободны, говорите по-английски, а мы будем вопрос по-русски.
Thank you so much for opportunity to give a talk. I'm going to talk about nodes and codification, and I wanted to start with some small manifestation of a list of terms, so that I hope one of them will find some reflection in your heart, and you find close to or interesting. So I will write a list of terms of things. So, for example, you would like to study threefold invariance, maybe Chern-Simons theory. Maybe you'd like to study conformal field series. Maybe WCW models.
These are 2D.
Sorry?
2D, 2D.
2D, yeah. Maybe you like process theories. Written, VGT, and so on. Maybe you like the brains, Calabi-Yau threefold, brains, Calabi-Yau, and some routine variants, cluster varieties. Viewers, maybe you like string chains, or even maybe various dualities, mirror symmetry, and so on. The funny fact is that all these various things, some in this or other way, are related to properties of various Napier states in some supersymmetric series. And another interlude or manifestation I want to make is to say what I would imply by categorification. What we might try to imply by categorification using this. So usually I have some supersymmetric field theory, and I have, say, well, and one supersymmetric field theory. I have some supercharge, and it's going to be. They satisfy some supersymmetry algebra. It's not very complicated. It's usually Hamiltonian as commutator plus some total charge. And for this such
how many charges is it important?
we need just one.
You have it already two, right?
Oh yeah, two. Okay, two is fine. And we like to define an index. That Newton's index is trace over all given space minus 1 to the f. This is for a number. And maybe I have some fugacities and charges commuting with the supercharges. I could add them to the index. And what say that this trace could be taken over not the Hilbert space, whole Hilbert space, rather only over Hilbert space of so-called BPS states. I'd say in a second what it means. For me, BPS state is a state. BPS state is a state with a function that are annihilated by both supercharges.
So you mean that this equality, that all other contributions just drop out?
Yeah. An observation that stands behind the categorification is usually that this dropping out of extra states is very similar to the Euler characteristic of a complex. So suppose I split all my Hilbert space into subspaces of fixed Fermat numbers. So I have C minus 2, C minus 1. This is the Fermat number. C naught, C1, C2, and so on. And my supercharges are raising the Fermat number and conjugate, make the opposite. And also, according to the Fortune decomposition, I could say that my Hilbert space, the HBPS, that is span of all psi such that psi, I mean this condition. This condition is actually isomorphic to the cohomologies of my complex with respect to Q. And the cohomological degree here is indeed around number. Then this property that I could drop all the other states except BPS states. It's trivial relation because that states that are not annihilated by supercharge, they come in pairs. So I have psi and psi, and they contribute to this trace. They cancel each other because of this minus 1 to the f. And we could see that this quantity is just Euler characteristic of this complex. So it's just sum over minus over I minus 1 to the I dimension of Ci. And it's actually the same as sum over I minus 1 to the I dimension of this H. And the categorification, the idea is to sort of refine a bit my discussion of the states, is to consider the actual Poincare polynomial of this Hilbert space, which is Hilbert space, and constructs polynomial that is sum minus I dimension which is I. This process we usually call categorification when we have some property that could be expressed as some with an index, and say that we instead we can start to consider the various states and within Poincare polynomials. So this is my categorification. And what naturally would ask why should we do this? Why we should do this? Why should we consider these very spaces? And the answer is that it is invariant under the modification of the supercharges when I could conjugate them by some operator. Q E minus O, Q dagger is conjugated corresponding to E minus O, Q dagger, E O. If I can calculate the the Hamiltonian now, HO, again, according to that formula, I will find that my new Hamiltonian is not the initial one. And the usual effect of such a conjugation is that I'm varying the coupling constants. So the index is naturally an invariant of normalization group flow, and correspondingly these spaces are invariants, at least their dimensions, are invariants of the corresponding normalization group flow. So this refinement
Just a vacuum state.
sorry?
You consider vacuum state.
Technically, it's not necessarily a vacuum state because I might have this extra contribution that is not non-zero. So it slightly lifts energy from the vacuum, technically.
But then not all supercharges should be after.
Yeah, both of them.
Нет, вопрос просто, если у вас ББ состояние, да, и в чем значит разница с вакуумом? Вашего рассуждения и простого рассуждения с вакуумом.
Yeah. Let me tell you an example. For example, example is vortices in, say, dimensional animals to theory. Vortices they satisfy well, vortex field configuration satisfy vacuum equation, and they are annihilated by the corresponding states are annihilated by both Q and Q dagger. However, if I calculate Z, it's something like R times integral times the flux. So in principle, energy of the vortex is non-zero. It has non-zero mass. So it's not ground state, but it's BPS state.
It's like instant.
Yeah. So you have learned what to do.
And so what are these four conjugation? What are requirements for this conjugation? Does it exist? When it exists? Should there be some local operator? Maybe not generally, but at least in an example.
It's a good question because technically, the problem is that when I conjugate by various operators, I modify the behavior of my fields at infinity, and in principle, I might conjugate operators in such way that there are no integrable field configurations, so on. So it's
Your consideration up to now is purely algebraic. So no infinity. It's not clear where you think.
Yeah. So usually it's done in the following way. We consider the supercharge for some known theory and conjugate it in such a way that it only modifies some of its some of the parameters.
Can you give an example?
Sure. Sure. For example, if I have some kind of hypermultiplet, usually, well, let's say I have say chiral-multiplet in four-dimensional. Well, let it be not four-dimensional. Let it be one-dimensional symmetric mechanics with n is 4. For some reason, and U in this case, if I have chiral-multiplet, it's given by phi, and psi I are supersymmetric partners. Now, supercharge looks like psi 1 d phi plus or minus one of the masses bar and psi 2 something like say sigma phi. Well, clearly I could represent this supercharge actually as psi 1 d phi phi plus psi 2 sigma phi, conjugated already by e to m square value of phi squared minus m phi squared. And furthermore, I can conjugate it by so here you could recognize if I say that psi is d phi and psi 2 is this inner operation of substituting vector d phi bar, you could recognize in this differential operator the Cartan model of equivalent differential for complex plane acted by rotations or scalings. And furthermore, I could conjugate it by something like e to the psi bar psi 2 lambda. That would rescale I think sigma to e to the lambda sigma. Example.
So in the first case, you have flow in mass.
Yeah.
And in the second, in this
It's a scaling of the sort of the vector field that is sigma phi bar. And I mean, this is a physical avatar of localization in the center of the complex plane that has an orientation of C. Right, so and in follows, I would like.
Yeah, and sorry, another question. This T parameter you have in the Poincare polynomial, what is its physical sense?
Just fugacity. Just a parameter. It doesn't have much sense. Yeah. Well, in principle, sometimes people try to assign it. Try to assign some embed the theory in higher dimensions, associate some rotation along some circle, and say that this is fugacity for that rotation. However, in such formulation, there is no clear meaning behind it. What we would like to study are, so again, another interlude, and we will try to study flat connections. On the complex plane. Flat connections will be given the differential operators, one will G AZ. A is just a holomorphic matrix, so it's A given G, L and C. And I think that dz bar is just dz bar. So they commute explicitly, so dz bar is 0, and this is a flat connection, so my exponent integral az dz. I should take it along some path. Let's call it path. So it's a function. It's a function only of homology class of this paths. This is class. So I'm able to make, slightly bend my path as I like, and the result wouldn't change. Why would why?
Sorry, why just the variable z take?
Z in principle belongs to some general sum Riemann surface. You might think it's just C. In principle, it's enough.
C should have some. You should have some functions.
Okay. Let's see. So why are we interested in this setting? Well, because there are various examples where we could apply this. The first canonical example is Schrödinger equation. So if I think of psi prime psi, H prime, it has this form here, right? The next example are various couple. Say in this case, I can think of again of my operator as being the dz squared minus stress energy tensor, acting, annihilating some conformal block. And the third example is Dmitry Galakhov equation in WW. It has the following form. So dza plus. Yeah, I have a WW model to level k in SUM. Then this equation looks like this: kappa plus n sum over v naught a eta ij is given form. And it again analyze conformal block that consists of insertions of my fields, so G lambda 1 of Z1, so on G lambda n alpha n Zn. And T acts on acts in some representations. Well, it acts on G as corresponding representation and corresponding generator. And if you look at all these examples under the slightly different angle, we would like to find the following similarity between those models. If I study here, I could study here WDB approximation or quasi-classical approximation. If I could study a limit C central charge of dimension going to infinity, and in the last example, if I study various knot invariants that are called polynomials, they are functions of variable q, that is, they are polynomial variable q, sum over a that are just actually integer numbers, and q, where q is e to 2 pi I over k plus n. I would find that it's also a natural setting when I try to consider here quasi-classical approximation. Let me see what it means. Quasi-classical approximation in this case means that if I redefine this parameter as 1 over g, like g here, or sorry, here was 1 over h bar. The usual one is also 1 over g. Here the right is 1 over b squared. It's also again 1 over g. And the quasi-classical approximation in this setting means that I take the limit g goes to 0. Then my Jones polynomial looks like exactly like some quasi-classical expansion. For example, if I try to in this approximation find the wave function that's solves my Schrödinger equation, it will behave in the following way: sum over some instantons or cells e to 1 over g s naught, the quasi-classical contribution plus s1 plus so on. And in here we see that it's just these two contributions and nothing else. So from this answer we see that for the problem to study knot invariance, this knot invariance is sort of quasi-classically exact in this setting.
So I missed everything. So what kind of statement are you making? So about KZ, it should be around critical level?
Not critical level.
So you say g to 0, it means that k plus n goes to 0.
Yes.
So that's critical.
Well, technically, since both of them are integer, it's hard to say what it means.
Hard to say, but opposite to k goes to infinity.
Yeah.
And what kind of statement about Jones polynomial?
Jones polynomial in this setting is quasi-classically exact. That's when I calculated, when I solve this equation by quasi-classical methods, it's enough to take into account the first correction, or zeroth correction, and the first one. And I could just simply draw the rest of this series.
What is a strict statement about that? Generally, you have a correction which is a tail in G.
Yeah.
You put G to 0. What to make with the first singular term?
No.
Long of G is not.
It contributes.
Say function.
It contributes.
Hmm?
It contributes as the. I mean the action in this case is proportional to 2 pi I to times some key. Key is not good. Times some m, and it defines the power of q. This approximation. And zeroth order defines this constant. Pardon.
So you say that the sum over A is the sum over saddles,
Yeah.
and so the Q is the contribution of action,
Yeah.
and the coefficient is the break point.
Yeah. And advantage of such a representation is that it's quite easy to categorify it. Let me try to explain how to categorify it in the usual sense. I would like
You can leave this and use another blackboard.
I see.
Especially if you need it after.
Well, it was just an interlude, and we already learned what it means to categorify something, right? So, technically we don't need it anymore. Again, now I'd like to explain what it means to solve, not to solve, yeah, kind of to solve this flatness equations, how to find the flat section of this connection in the limit g goes to 0. There is standard techniques. Let me briefly try to remind them. And when we see this technique, we will notice immediately how some categorifications enters the story quite naturally. I can consider the Gish transformations of my matrix A, of my connection A, it's U, UZ, A, U, inverse plus, minus GU, Z, inverse, and the limit G goes to 0, I neglect this term and technically diagonalize my matrices A, Z in each point Z of my Riemann surface. And the solution, so psi equals to UZ inverse psi.
And why are you not able to do that simultaneously at other points?
Because in the limit, I kind of neglect this extra term. Technically, I cannot. but this is point of the street, right?
Yeah, formally you can, if G is exactly 0, just you have the transformation at each point.
Right, but I would have the divergent part. So if I say that the exponent of my 1 over G integral A of Z dz is diagonal now, it's U, so Z1 to Z2, and diagonal matrix E1 over G integral of P1 Z, and so on. Integral of 1 over G integral to Pn of dz. Here, C1, where P is Pn, Pi are roots of the characteristic polynomial for A. And Pi are roots. And everything started quite smoothly, however, we sort of immediately observe the problem coming from the differential points for this. Well, actually, it's curves. So that is some cover of my initial Riemann circle. So we get differential points, and from the differential points, I have sort of an immediate problem that I say I define my solution psi at this point. It's some exponent of e plus e integral p minus dz times some vector. And if I go around this brushing point, my psi this p plus and p minus becomes sloped. So it's e equal p minus dz, p plus dz. So I have a contradiction with my in my Cauchy theorem that in some neighborhood of a point I have a single solution to my problem. I have presented already two solutions that are different, and they are both they both are valid in this neighborhood. And solution, the usual solution, lies in the dividing the surface by Stokes lines. And I say that on the Stokes lines is defined by the constraint that 1 over G E1 minus E2. There are two roots. Z belongs to non-negative real number times some ds the s is parameter along the Stokes line and this defines me Stokes line for Stokes line gun. And they start from the breaking points, and say that if I have again the breaking point, this is the cut, this is my Stokes line. If I intersect this Stokes line, along the Stokes line, this difference of solution is exponentially small. So physically, I kind of haven't noticed that exponentially small part of the solution have mixed to my initial solution. And we have a rule that if I intersect the Stokes line, the solutions jump in controlled way. So I get psi1 plus c psi2, and psi2 will remain the same. And a nice way to define this second solution that I should add to my initial one is to consider what is usually called the detour, and if I add to my contour an additional contour that encircles the breaking point, then along this contour the solutions exactly swap between each other. So if I draw this picture in CD, it looks like this. So I have two sheets of my cover. So they intersect somewhere. So this is branching point. And I have two initial paths. So this is just simply psi1 and psi2. And I have extra terms that correspond to encircling this breaking point and ending on another sheet. So I go like from one sheet to another. It's not hard to calculate this. It's not hard to calculate this coefficient from a simple constraint that the connection is flat around the breaking point. So let me write this constraint somewhere. Maybe don't need this one. Or maybe I write it here. So I have my breaking point, my cut, 3 Stokes lines. Let me not tell you why there are 3 of them, but try to believe me. And I have to two paths, and so encircling this branching point. And I want to have a constraint, to derive constraint when the parallel transport along these two paths is equivalent to each other. No. Yeah. So I have three detours, gamma 1, gamma 2, gamma 3. And if I write them in the matrix, I have this constraint is the following. So first I encounter detour along the gamma 1. It looks like 1 gamma 1 0 1. And I haven't said that if the Stokes line is of specific kind, so it allows me to go from say sheet 1 to sheet 2, but not the other way. So it's of type of 1 2. Then if it's this Stokes line of type 1 or 1 2, then this is of type 2 1, and this again of 1 2. So if I go further, I should my Stokes coefficient enters opposite part of this matrix, and I want this equality to be equal when I cross the card. It simply solves my sheets of my cover, so it's this permutation matrix, and this gamma 3, so it's 1 gamma 3 0 1. If I multiply matrices, I find that 1 gamma 1 gamma 2 1 plus gamma 1 gamma 2 equals what? Gamma 3 1 1 0. Technically, if we draw this picture into dimensions and draw all these detours and paths on it, we will find that actually if I go just simply along, say, sheet 1, along this path is the same as well, technically it's clear, right? So for example, if I go along this path on sheet 1, then this part with gamma 3, it means that I go along this path, then circle the branching point and go further. So it's technically the homotopic paths. So these parts are actually all homotopic except this one. And it reduces to the following relation between the paths on the cover. So such path plus another path that goes in circles and goes further back equals 0. From here, actually, we could immediately see that this C should be 1, and that actually the calculation of the WB approximation actually ensures this relation. So,
but I already didn't get your relation between matrices. What does it mean? No, can we just solve it?
Well, it's a constraint that the parallel transport along these two paths
I
are
understand, but what it gives for gammas?
For gammas, if I write them explicitly, we will find that they are actually equivalent. This unit implies
from your formula, it literally means that they're all unities.
I should write here some paths. They are not just unities; they are connected with the. I'm sorry, this is a very bad notation, actually. Technically, this matrix is just matrix of Stokes coefficient in this point. But to construct actual paths, I should glue these matrices with these tails. If I
transport matrix.
yeah, if I do so, I will find that actually all these paths sitting in these three angles of my matrix are equivalent, except this one that gives me constraints that I should solve. And if I draw these paths on my cover, I'll find that actually it implies that path that just passes by, and a path that makes a loop around the branching point should sum to 0. And this is actually true if I now write a formula for the flat section. So let me denote it by psi. Psi behaves as exponent of g minus 1 integral of this p on some sheets z plus g naught integral of certain form omega. Omega is defined in the following way. So if I have a root I of my matrix A, then I have corresponding eigenvector of my matrix A, and then I define omega as minus psi 1 on sheet I. So psi 1, psi 2, and so on, give psi I, and so on. Divide just by psi 1, psi 2, and so on. This notation implies that I could just simply have a column I have my vector column, and I organize them in the matrix and take a determinant.
So omega is one form.
Omega is one form.
Because of this extra d.
Yes. Yeah, so I can integrate it, and it gives me exactly what we would expect, because if the branching point P, this rule behaves as square root of z, so I have plus square root and minus square root that are these two sheets, and omega behaves as dz, well actually it's equal, dz over 2 z. And the difference between these paths, so it's, if it's gamma 1 and this is gamma 2, so integral of omega along gamma 1 along gamma 2 of omega is integral along gamma 1 of omega plus pi I. And if I substitute them in this formula, I will find that exactly this loop gives me minus 1 in the summation. And this relation should remind you that relation about the categorification and the all the characteristics of complexes that I have already erased.
How it reminds it? What
it reminds that in a way that this integral of omega is a fermion number. So when I calculate the WQB approximation in this formula, I explicitly substitute the fermion number as let me write the let me draw this diagram. So suppose I have a path on my sigma that starts at point z and ends at point z prime. And we would like to construct the product transport along this path with a given connection. We said that in principle we do not know how to do this explicitly. We calculate it in the WQB approximation and use this little rule. To get a set of homotopy classes of classes path Z prime, and my covers of cover sigma the tilde. That are not homotopy invariant of my initial path P. Then I use this formula to map these paths to numbers, and I map it to number. So it's some number, some number of pi i's times some coefficients, exponential contribution of something divided by g. And this number is actually invariant of P. Because this constraint is satisfied. However, I could, instead of mapping to the number, I could simply try to eliminate this constraint, the path related by this constraint, because as I see, in principle, as I see, this is enough for my path, for my construction for this set of paths to be homotopy invariant of my initial path P. So we could construct a complex of paths. We grade each path by Fermat number. A Fermat number in this case, a number in this case is integral of omega. And we could construct the differential or the supercharge that maps this path to this path. And construct corresponding to homology. And this homology would be invariant again of P. And if you go this way, so this will be categorification.
This operator Q is not defined on what space?
On space of paths on sigma, on the cover.
It's infinite dimensional space. It's better to know.
Yeah, in principle. Actually, I would, technically no. I would like to have this path, this space. This is space of homotopy classes of paths connecting Z and Z prime related to this cover sigma. Physically, this is simply the two-dimensional. So I'm out of time already. Okay. Let me say some physical words. Physically, this is all simply two-dimensional 2,0 theory. 2D to n equals 2,2 one-down unit theory.
Where on sigma or of maps to sigma. How it is related with the geometric picture?
Technically, it's not related. Initially, if I have a space of parameters, I could construct the superpotential W. So these are fields. These are fields, and these are parameters.
It's different Z from what you had before.
No, this is the same Z.
It can be many parameters.
It could be many parameters. In this case, in this case, I would like to consider the parallel we could consider a trajectory in the space of parameters and pull back my connection to this trajectory. It will be again one parameter. Right. So in this setting, the physical meaning of this geometrical construction is quite transparent. Indeed, the integral of omega is simply the Fermi number of corresponding state in this theory, and the intersection with the Stokes line is a solitonic solution in this theory. And the action of the supercharge is an instanton of this theory connecting to solitonic.
Probably it depends on particular superpotential.
It depends on the particular superpotential.
And so how superpotential is connected with the
connection is somewhat not so straightforward. In this theory, I have this ring of chiral operators. That is just simply, I could think of them as polynomials in field phi modular various derivatives of dw. Then in this ring, I have structure constants, gamma on gamma, and then multiplication by dz of w. It's again some operator in these terms. Then multiplication by on various operators of alpha would give me a connection alpha beta or beta. So it's not so straightforward.
But this matrix E
Is that A?
is that A.
Yes.
And so, and where are branch points?
Bridge points are where the vacuum different. Well, I mean, I have distinct vacuum in this theory.
So just the roots of W coincide.
Yeah. Of dw.
For some particular values of Z,
Yeah.
we have this sort of degeneration and
Yes.
this is reasonable branch points.
Yeah. Exactly.
I see.
In principle, it's the easiest way is to do this for the area function, where there is a single bridge point. Area function is just a cubic theory, phi cube minus z5, 1/3 minus z5. It has two vacua. When z equals 0, they collide, and the Stokes line corresponds to this. This soliton, right? So something like 11 tau. Wow. There is simple solitonic solution in this model that corresponds to the Stokes line. And the story also is related to the case of the Morse theory. When on my field space I introduced this kind of funny height function that is integral over real part of phi bar plus w phi x dx. That's one. Yeah. Well, since I'm running out of time.
But just about this formula. So you had before just one phi, Yeah, the space of fields and blah, blah, blah. So here you have this 5 bar, yeah? What does it mean?
It's conjugation.
So you just introduce it formally. And who is X1?
Yeah, it's two-dimensional field theory, so I consider. Sorry, I again jumped just ahead of myself. I should say that we can to put this theory in the framework I have discussed so far. We have to say that our quantum field theory is simply supersymmetric quantum mechanics on the space of maps from space to fields. This is two-dimensional one-algebraic theory, so space is one-dimensional. So I think just of leave of whole sheet of my theory. So I have x0 time running upwards, x1 running horizontally. So my wave functions are functions of functionals on functions of x1. Functions of x1. Not in this setting, I could construct the supercharges. Supercharges are simply conjugated by each integral on the x1 operation with respect to phi times some fermion side. Say 1 for x1 minus h, and h is this height function. And this is a story about this Morse function that
sorry, in this definition of this h, you have integral over x1 and you have integral in phi space.
Well, I could say this dx.
But where from it comes, what's the meaning of this h function? What should it satisfy?
It should be Morse at least.
How do you see that it's Morse?
See that it's Morse. I think it's enough for the superpotential to be Morse. It's a good question. However, in principle, if I start with this one-algebraic theory, I could write the Lagrangian, could calculate the supercharges, and I'm able to represent the supercharge in this form. It's simply like this. Nothing mysterious.
One of the charges.
Right. I have to choose a specific combination of two charges, and one of them is just simply this. And again, this geometrical picture would be simply calculation of quantum numbers of my solitons that appear in this theory. Integral of omega would be for a Fermion number, and integral of p would be the central charge, I think. Right, yeah. Central charge. So, how is this all related to nodes? And why?
And sorry, Jim, I also didn't get what sort of categorification. Because before we had just some function which is a combination of dimensions, and categorification is what? When you force it to depend on some other parameter.
Yeah.
What do you mean by categorification in this picture?
So far, we could have robbed this bullshit in a cylinder, and for us, the path integral would calculate the index of this theory. However, right now we start to get interested in the Hilbert spaces of themselves. So we distinguish various Hilbert spaces, and they are graded by two numbers: the central charge and Fermi number. And the index simply gives us the signed sum of these dimensions. And right now we distinguish them, well, each one.
Can you write down the formula? Central charge is just the central charge of this theory, or?
Yeah. So for a soliton that interpolates between two vacua, phi1 and phi2, central charge is just simply a difference of the values of the superpotential in these two vacua fields, phi1 minus w, phi2, phi1. So in principle, I might have various various solitons interpolating between the same pair of vacua. So this soliton, maybe something else, and the index gives me a sum over solitons interpolating between the same vacua, phi1 minus phi2, minus 1 to the f from the number. Well, we get and now we refine this formula by saying that we consider actually the vector of so I have a vector of number of solitons of central charge z, or interpolating between phi1 and phi2, and central charge and Fermi number f. This is the refinement.
And for this very simple theory, yeah, so
For this very simple theory,
it's abelian, yeah, so you have only one field.
yeah.
So
Yeah.
A is just a number, yeah?
A, you mean
Matrix, A matrix.
matrix A? No, it's not just it's 2 by 2 matrix.
It's 2 by 2 now.
Yes. Yeah.
But you have so
Round ring is two-dimensional.
huh?
Round ring is two-dimensional, right?
Ring is two-dimensional. So it's unity and phi.
Yeah. So
Ah,
yeah, unity phi.
Unity and phi, yeah, you have unity. So. And so, can you write down the answer?
For the matrix,
For everything.
0, 1. Then if we'd like to study solitons, we need paths. So solitons are simple. Solitons.
This big Z is something like small z in the power 3 over 2, yeah?
No, it's A of z.
No, I mean this big Z central charge.
Central, yeah, it's
It's just
z half. What else?
And so this omega, how you compute it?
Omega is just dz over d, dz over 2z.
2z, so in this 2z comes from square root of the 2z.
Yeah.
Somehow, yeah?
Yeah, exactly. So for these two paths, its integral should be to pi I, the difference. Should be, sorry, pi I. So in exponent it gives -1, and these paths cancel each other. And yeah, this is, this is exactly geometrical description of this simple area.
Where you have one branch point and
Yeah,
cut goes to
exactly.
infinity.
Yeah, exactly. Yeah. And you can see that I could also even draw what is this constellation. This constellation is that I have to vacuum phi plus minus z 1/2, and this constellation is coming from two.
So the question is, what is the classical limit of the field? I'm trying to ask
Which one? The
Зависит от какой ты хочешь классический предел, по какому параметру.
Тот, в котором солитон есть.
For example, I could rescale the whole superpotential. Just rescale it. So the size of solitons, well, size of soliton is something like 1 over W prime absolute value.
But so by soliton you mean something like king here.
Yeah, it's exactly key. So,
зависящий от одного параметра, который из вакуума идет в другой.
So this one is just simply solution when I have, so this is my x1, right? This is my field phi. So it's constant vacuum. See, phi plus, and this is that one. Let me say this one is that one unit. And if I have phi minus, then that product gamma 1 gamma 2 is king anti-king configuration. And that Q is actually saturated by an instanton. If you'd like to draw it in 3D, let me try to draw it in 3D. So I have time x0, x1, and x1 and phi, and I have two configurations when it's just simply phi plus and phi plus, and here I have a king. And the instanton is if you could imagine, it's such as 3D leaf that have a hole, and this hole just.
Инстанton, что вы называете теперь?
Instanton is an interpolation between two soliton solutions. It's instanton because instanton is in the sense of the Morse theory because the flow it's a solution to the Morse flow. So if
is it a holomorphic map from some?
It's not holomorphic.
No holomorphic.
Because in this case it becomes not holomorphic. Technically it's holomorphic when W is 0. If it's W is not 0, we could find that the map looks like I should rotate it, so it's D2 plus or minus ID1 x phi is minus d phi W conjugated.
Excuse me, what king anti-king configuration looks unstable?
It's only loose, unstable, but technically in the presence of what is called interface. So I allow my parameters to vary along the spatial direction x1. So it's Dex as additional extra force source in the soliton equation. So it so they allow them to sort of be attracted to fixed points. So the king configuration is stable if they are located at specific points where my path intersects the Stokes lines. So I know exactly where the centers of masses of the solitons are, one next to.
So you break translation of invariance, right?
Sorry?
You break translation of invariance.
Yes.
Yeah, just by introducing space-dependent coefficients in the action.
Actually, even by choosing some specific supersymmetry, because my supersymmetries, right, will commute on sigma that mu, right? I have to when I break the translation symmetry, I break some of the supercharges. So it's not the completely supersymmetric configuration. It's half supersymmetric configuration.
Half BPS.
Half BPS, yeah. I
Because
did use
king is half BPS.
king is half BPS. Yes. So technically, what this Anton does, it allows this king and king to collide and create boring bounding. Notes.
You can finish trying to make some statements.
Okay, let me make statements. Why notes? Why notes are well?
Не стирайте, у вас счет на чистых досках.
Why?
Так можно опустить, это поднять. Просто сделайте на нем
So what about notes? Notes. Technically, first of all, we could start not from with the nodes. Rather, we would start with the representation of the braid group. So you had a nice talk by Alyosha Slipsov, so you know everything about braid groups. Braid group is created by two types of braids. So I have multiple braids, multiple strands, and in these strands I introduce two braid elements, this one and this one, and they correspond to the R matrix, the inverse R matrix in Q. So then, algebra. And physically, I could represent this R matrix and inverse R matrix as ordered exponent of integral of Kinshik homologic of connection. Kinshik homologic of connection, and as we studied, discussed this Kinshik homologic of connection, we could calculate it quasi-classically. And as I said, it's enough to calculate them quasi-classically to calculate the invariance of nodes. In principle, it's enough to calculate to the R matrices that are entries of R matrices are polynomials in Q, and they are also quasi-classically exact. And furthermore, we could categorify it. Verify it in the natural way by constructing by considering the same story for this connection. Here we could write down some explicit expressions, quite nice. So if I'm interested in quantum SL2, and I would like to consider conformal blocks living on the cylinder with some non-integral weights, lambda 1 and lambda naught, and lambda 1 corresponding to 0, say, and infinity, and I put some fields of spin 1/2 along the cylinder. If I start to braid them and apply the digital logic of connection to braid these points, I would derive the R matrices. And this corresponds to the Landau-Gizmo theory with the following superpotential. That is sum to m-1. Say I have m punctures, so it's 0. So all of them are 1/2 spin half, and it starts from Z1 and goes to Zm. Minus lambda naught over 2 log ZA, minus 1/2 sum over Z B, and minus 1 log Z minus ZB, plus sum I to 1 to the n, lambda naught log phi I. Plus mutual interactions. So naught to minus 1 and log. Actually, it's very easy to derive this superpotential if you think that your conformal block is a partition function, right? So the ordinary situation, non-categorified situation, is just index or a partition function of specific manifold with periodic boundary conditions for fermions. So technically, if I am able to represent my conformal blocks as partition function of something, I sort of solved the problem. If I could categorify the partition function, and if I consider Hilbert spaces, I would automatically get categorified invariance at least of braids, categorified representation of the braid. And in principle, if I consider the partition function on a disk, it's a disk, so but it's a little bit curved. If I consider partition function of my n equals to two-dimensional and Landau-Gizmo theory with this superpotential, the partition function would localize to integral of dphi I of exponent some parameter w. And in this expression, you would easily recognize the free-field representation for conformal block of corresponding WCW model. So superpotential is easy to define.
What is small m?
Sorry?
The number of phi's. What is this number?
Yeah, n is the number of phi's. It's defined in the following way. So.
So it has nothing to do with the ramp. Ramp is 2.
Rank
Is 2.
Yeah.
So it's something else. I see.
N is different. Let me tell you how to define it.
Is it the number of string fields?
Yes, and since the R matrix leaves invariant the weight of this conformal block, so n is actually the weight of conformal block. So if I put some m spins up, then m minus n spins down. So So the number of spins that are up would remain invariant during this braiding. And then it's defined as this way. And the statement is that if in principle we codify the story, we codify the our matrix, we would derive the codified representation of the braid group that is known in mathematics, K algebra. And if we construct the node invariance, we would derive famous Havanov invariance. There are various details related to the fact that actually there are various singularities induced by these logarithms that would not allow me to distinguish various solitons. However, this problem might be cured by considering more higher energy superpotential, because logarithms in this setting are results of one loop corrections to the superpotential. So we introduce back the fields that produce these loop corrections. We would resolve that problem, or another way to do it is to consider mirror symmetry and map these Landau-Rubin theory to to theory on flux. Okay, maybe if my time is up, I think I should stop somewhere, maybe for this point.
Спасибо.
Yeah, Dima, speaking of node invariance, I mean, does this W provide us some, I don't know how to say, some way to compute the node invariance? What should we compute having this?
Technically, yeah. In principle, if you calculate the R matrix, for example, so this element, you would derive the R matrix of quantum SL2.
Yeah, but I thought that the R matrix is known. No?
R matrix is known, yeah, sure.
Why should we bother to invest some new representation for it if it is known? Or probably I just misunderstood it. If it is known, why do we need any of this?
Yeah, so
plug it into mathematics and compute.
Yeah, sure. So the point is that for how many decades? In principle, the initial interest was to construct the physical model for the categorified invariance or categorified braid invariance. And the story is somewhat rather simple, that we represent our known results, like our matrices, in the form of Euler characteristic or index of some theory. Then we, from this Euler characteristic, we go to the cohomology of some complex, or physically we go to the counting actual BPS states. And we will find that this indeed categorifies or refines our node invariance, so it adds more information to this.
Sorry, I don't see where is the refining parameter. I probably missed it. There should be a parameter which is responsible for refining.
Well, the simplest way is that you see, for example,
so that G,
the Fermat number.
Fermat number.
So in principle, if I have two states of Fermat number 0 and Fermat number 3, they in the index they annihilate with the same other parameters. In the index they annihilate each other. However, in the Poincare polynomial, they would give you 1 plus t cube. And we know that there are two states, so more states than.
So you see, the parameter is dual to Fermi number. Yeah, you just sum up.
No, it's just exactly the Fermi number.
No, Fermi number is its power.
Yeah. Well, you could say it's fugacity for Fermi number. I was struggling to say this in the beginning because, in principle, there are theories when we explicitly couple Fermi number or R charge to the some fugacity and try to construct the some partition function by localization in the usual way. It seems that in this setting it does not work. We have to calculate actual Binet spaces, calculate actual action of the supercharge, instantons, and things start to get ugly actually in this route.
Еще вопросы? Okay, so let's think this